Hey guys, today I'm going to discuss my codes on machine problem 6, which talks about linear and nonlinear regression. For this demo, I chose problem number 1, which is the Andrews equation. So, Andrews equation is an empirical model that relates temperature with viscosity. So, mu is equal to dE raised to P over dA, where mu is the dynamic viscosity of water, dA is the absolute temperature, and P and D are constants. So, here we have following data for water. First row talks about temperature 0, 5, 10, 20, 30, 40. And then the second row is the mu, right? The dynamic viscosity. So we are asked to predict the value of mu if the temperature is negative 10 degrees Celsius. So we are asked to write a method script to solve the problem. And then first using linearization of nonlinear relationships. And then second is using the fit function as we learned in Math Academy. So let's go now to my code. As usual, the CLC clear close all, and first is the data. As you can see, the temperature is increasing and the mu is decreasing. So for the first figure of my code, I talked about the plotting of the original data, which is just the plot function in ts x and as y. I also use OA for the markers. The x label is temperature, the y label is mu, which is the dynamic viscosity of water, and the title is the temperature dependence of viscosity. For the second figure, I use the fit function to plot the data. It's the same um, labels and so on. For the third is the linearization. So first I solve for TA, which is the conversion of Celsius to Kelvin, which is just the given Celsius plus 173.15. And upon linearizing the equation, the new values became y is equal to log of mu. I use the logarithm to linearize. X is equal to 1, that TA, 1 because x vector, and then I use the scatter plot with the label. So this is the linearized plot. And for the fourth figure, I fitted the linearized plot. So it's the fit function once again, poly, and of course hold on. And we want to know the value of the coefficient if we want to predict the value of mu. So the intercept is from the fit function. So function d is the exponent of the intercept and slope function, and of course b is equal to the slope. for the fifth um, figure, uh, we now use the uh, linearized, I'm sorry, non-linear regression. So the concept of non-linear regression. We use this. And lastly, for the prediction. So we want to predict what happens to the dynamic viscosity if the temperature is negative 10 degrees Celsius. So in order to do that, we use this equation. We use T and this equation. So T E raised to E over TA. This is TA, the conversion to Kelvin. And we plot what we the two values here. Okay, marker face color is K, the limits, and the legends. And let's see if this works. Right, so we have 5 figure. Figure 1 is the plot of the original data. Figure 2 is the fitted plot. As you can see, it goes down as the temperature increases. The value of the dynamic viscosity decreases. So as the water gets hotter, it becomes less viscous. And now for the third figure, the linearized plot, using the u values of x and y. And then we fitted that plot. As you can see, it's more closer. The data are closer in the linearized plot. And here we predict the value of the dynamic viscosity of water when it's negative 10. So we already expect that the value will be higher because, as we said, as the temperature gets hotter, the water becomes less viscous. So as the temperature gets lower, the dynamic viscosity increases. Here in the command window, you can see the values of the function and the goodness of the fit. We have 0.9541, which is a pretty good fit. So the temperature negative 10 degrees Celsius or 293.15 Kelvin, which is the TA. The mu, or the dynamic viscosity of water, is equal to 2.3603 times 10 to the negative 3 Newton second per meter squared. That's all. Thank you.